Okay, we're going to work some two-body force problems today. There's a little something new in these problems that makes it a little bit new, but I think it'll be pretty easy if you pay attention. So, for example, the problems that we're going to work today look something like this right here, okay? Where you've got two blocks, and you have an applied force on one of the blocks. And so this system right here is going to accelerate in the direction of the net force. So we're going to draw free body diagrams, which we're familiar with. We're going to put in all the forces and find the magnitudes of all those forces. But there's one force that's new to these problems, and that's right here. Okay? There's a contact force between these two blocks that we have to kind of figure out how to work the physics of that. And so please pay attention as we're going through these problems today. And so hopefully you have your guided notes out, Chapter 4 guided notes, and be writing down everything that I write down. Okay. All right, so here's an example problem. It says Tony pushes block A, which is 10 kgs. So I'm going to put 10 kgs in this one. He pushes it to the right with the 100 Newton force. So that applied force here is 100 newtons. And block B has a mass of 15 kgs. The coefficient of friction is 0.2, so we're going to have to use that to find friction. And it says find the acceleration of the system. We want to know how fast these blocks are going to accelerate if he pushes on it with a 100 Newton force. Okay. So what I would like to see you guys do when you have a problem like this, a two-body force problem, is to draw the free body diagrams for the blocks separately. So, for example, we're going to draw the free body diagram for A by itself. Then we're going to draw the free body diagram for block B by itself. Okay? So I'm going to draw the free body diagram for block A over here. This was 10 kgs. Now let's put in all the forces that we know. Where do we start, guys? Where's the easiest place to start? Weight. Okay? So weight is equal to mg. 10 times 9.8, good, is 98 newtons. All right, now, guys, is block A moving in the vertical direction? No. It's not. It's at rest. So according to Newton's first law, the normal force has got to be what? 98 newtons. Yeah, these have got to be balanced. It's not moving in this direction, in this axis, so it's got to be balanced. All right. Now, let's draw a force to the right. What's pushing block A to the right? Force applied. So let's label it force applied. And its magnitude, it told us, was 100 newtons. Now, let's go to the forces that are pointing to the left on block A. What's a force that's going to the left on block A? Force of friction, okay? Let's find its magnitude. So that's force. Remember, guys, force of friction is equal to the coefficient of friction times the normal force. So let's take 0.2 and times it by 98. What is that? 19.6 is the friction. Okay. But there's one more force that's pointing to the left on block A. What would it be? Yeah, there's this contact force right here, right? So, isn't block B going to push on block A to the left? Isn't there going to be a force to the left? Yeah, and I'm going to call that, and this is new, guys, so please watch. I'm going to call that the force that B puts on A. So FBA, the force that block B pushes on block A. Does that make sense? Force that block B puts on block A. Now, can I find its magnitude? I can, but not right now. So we're just gonna leave it as the force that B puts on A. Now, let's come over here on this side and draw the free body diagram for block B. Okay? So here's block B. It was 15 kgs. Again, let's do force of gravity down. which is equal to mg. What's 15 times 9.8? 147? Thank you, Clint. And that means my normal force is what, guys? 147. It's got to be balanced because, again, block B is not moving in this vertical direction. So according to Newton's first law, if it's at rest, it's got to have balanced forces acting on it. Okay, now let's go to the right. What force is pushing block B to the right? But it's not the force applied anymore, is it?
No.
Because the force applied is on block A.
It's the force that A exerts on B.
Good. It's the force that block A exerts on block B. So I'm going to call it the force that A puts on B. Please use that notation. You can see that in physics textbooks all the time. Is there any other forces that's making this block B go to the right? There's not. Okay, now let's get the forces that are making it go to the left. Okay, so we know that force of friction opposes motion, and since he's pushing it to the right, force of friction is going to go to the left. Let's solve for it. What's 0.2 times 147? 29.4 newtons. Okay, very good. Is there any other forces that are pointing to the left on block B? There's not, is there? So that's it. So when you get to this point, you've drawn them separately. We don't have the magnitudes of this contact force right here. Okay? So let's talk about that for a second. Let's just talk about it right now. If this contact force right here, guys, this is so let's go to this one. The force that block A puts on block B is going to the right. But let's look at this one. The force that block B puts on A is going to the left. How are their magnitudes going to be related? Are their magnitudes going to be equal? Think about Newton's third law. What did it say?
Equal and opposite.
Forces occur in pairs, and for every action there's an equal and opposite reaction. So the force that A puts on B is equal to, but opposite, the force that B puts on A. So even though I don't know their magnitudes, their specific magnitudes yet, we know that they will be equal, right? But opposite directions. So, okay, let's go to answer the question that was asked here. It wants to find the acceleration of this system. Whenever you see the word acceleration in one of these force problems, which one of Newton's laws are you thinking about? Which one is that? Second law. So let's write that down. I'm going to do it right here. So force net is equal to ma. It's Newton's second law. So let's find the net force. Since he's pushing it to the right, I'm going to say that everything to the right is positive. Everything to the left then is negative. What force is to the right on both of these blocks?
Applied.
Force applied. Okay, so 100. Now, if that's positive, now everything to the left is going to be negative. Oh, but wait, wasn't there another force? The force that A exerts on B. So let's put that in there. So plus the force that A puts on B goes there. Now let's subtract off everything that's negative. Okay, I've got friction here. So I'm going to minus 29.4 from friction there. I'm going to minus 19.6 right here, minus 19.6 there. And I'm also going to minus the force that B puts on A. Okay? And all of that is going to be equal to the mass. What is the mass of this system, guys? If block A is 10 kgs and block B is 15, what's the mass? 25 times the acceleration, right? That's going to be your ma. So, when you get to this point, now look, we have 1, 2, 3 unknowns in one equation. Can I solve it?
No.
I can't. So, what are we supposed to do here?
Wouldn't they cancel out?
Good. Yeah, these contact forces are going to cancel out, aren't they? the force that A puts on B, isn't that equal but opposite the force that B puts on A? Yeah, so if one's positive and one's negative, they cancel out. So let me rewrite this so I have a little bit more room. So now we have 100 minus 29.4 minus 19.6 is equal to 25 times A. That's kind of the important point of these problems, is to realize that the contact forces are equal but opposite, so they can and will cancel out when you get to the net force. Okay, now we've got one unknown in one equation, so we can solve it. Let's simplify it. 100 subtracts 29.4, subtract 19.6, and that's 51, is equal to 25 times A. How do we solve for acceleration? Divide both sides by 25. So the acceleration of this system is equal to 2.04 meters per second squared. So that's the acceleration of the system. Is block A going to accelerate at 2.04 meters per second squared? It is. It's going to move to the right. What about block B? Since they are connected, they are going to move at the same rate, 2.04 meters per second squared. Okay. Pretty easy, right, guys? That's pretty easy. But hey, let me ask you this. What if they asked you to solve for the magnitude that block A puts on block B? Now that we know acceleration, can we plug this back into Newton's second law on just block B and solve for it? Let's do that real fast, okay? So I'm going to use Newton's second law just on this one. So force net is equal to ma. Let's get the net force. Isn't the force that A puts on B going to be positive? Now let's subtract off everything that's going to the left. So minus friction, which was 29.4, is equal to the mass of it is 15 times its acceleration we just solved was 2.04. Okay. So let's take 15 times 2.04. It's 30.6. And then what am I going to have to do with this 29.4, guys? Add it. So let's add 29.4. So the force that A puts on B is equal to 60 newtons. Okay, now what if they asked you this? What if they asked you, what's the force that B puts on A? You could plug it in, but do we know it? If we know one of those, isn't this one going to be 60? Remember Newton's third law? For every action there's an equal but opposite. Is this one going to the left? Yeah, and the other contact force was going to the right. So this one's positive 60. This one would be a negative 60 if you were to plug it in. That's the only trick with two-body force problems, is that contact force. It's pretty easy, isn't it, guys? Let's see if you've got this. I've got a practice problem number 20. It says 3 boxes of mass M1 has 4 kgs. MB is 5.5 kgs. And MC was 10 kgs. Are side by side on a flat surface as shown in the diagram below. A force of 120 newtons, so the supplied force is 120 newtons, is applied horizontally to the 4 kilogram block. That's MA here. And it gives us the coefficient of friction is 0.25. Guys, I would like you to try this one on your own. Let me kind of walk through the steps. Again, you're going to draw the free body diagrams for each one of these blocks separately. So I want to see MA's free body diagram separate from MB, separate from MC's free body diagram. Once you've got the free body diagrams, find the magnitudes of all the forces that you can. And then in the end, you should be able to use Newton's second law to figure out the acceleration of this system. So here's the couple things that I want. Okay, I want 4 things actually. Draw the free body diagrams for each of the 3 boxes separately. Find the acceleration of the system. You're going to use Newton's second law there. I want this contact, the force that A puts on B, and I also want the contact force that C puts on B. See if you can do that. So please, if you're watching the video, hit pause. Try to answer those questions and see if you can get them right. Once you have an answer, then hit play and see if you got it right. Okay, so let's see how you guys did. What I've done is gone ahead and drawn the free body diagrams for block A, block B, and block C. But I've left off a few of the important forces, the new forces that we're talking about today. So, guys, let's look at the free body diagram for block A for a second, which I've drawn right here. We've got an applied force of 120 newtons. The force of gravity was 39.2 newtons down. That means the normal force was 39.2 newtons up. If you're pushing this system to the right, friction is always going to oppose motion, so I've drawn friction to the left. So if you take 0.25 and times it by 39.2, you should get 9.8 newtons. But there's another force that's going to the left on block A. What is it, guys? Yeah, it says contact force. Good. So let's call that the force that B puts on A. So I'm going to draw that going to the left as well. We don't know its magnitude yet, but we'll be able to solve for it later. So let's go to the free body diagram for block B now. Okay, I've drawn the weight, where the force of gravity was 53.9 newtons down, which means my normal force was 53.9 newtons up. Again, because it's at rest in the vertical direction. It's not moving vertically. So the forces have to be balanced. I know that if this system is moving to the right, that my friction is going to point to the left. And I found friction by taking 0.25 and timesing it by the normal force, and you should get 13.5. But guys, there's another force that's going to the left on block B. What is it? Yeah, it's this contact force. So I'm going to draw that in now. The force that C puts on B. So I'm calling that the force that block C puts on block B. What force is it that's making block B move to the right, though? So what's making this block move to the right? Good. It's that contact force that A puts on B. So I'm going to draw that in. Again, I don't know these contact forces magnitudes yet, but we'll be able to solve for them later. Let's go to block C now. I went ahead and draw the free body diagram. We got force of gravity, which is 98 newtons down. Normal force means it's 98 newtons up. Force of friction, I took 0.25 and times it by 98 to get 24.5. But what is making block C move to the right? Good. It's this contact force right here, the force that B puts on C. Is there any other forces going to the left on this block? There's not, because there's not a contact force here. There's not another block out here that's going to put a force to the left on that. So that's it. How many of you guys got the free body diagrams correct? Very good. Now when we get to that point, now we're going to solve for the acceleration of this system. Okay? So we're going to solve for the acceleration. Whenever you see the word acceleration, you think force net is equal to ma. I'm going to call everything to the right positive, and everything that's going to the left negative. So when you look at our forces, everything to the right is going to be positive. Okay? And everything to the left is negative. So I've got a positive force here of 120 newtons, so I'm going to put that in for the net force, 120. I've also got this force that A puts on B. But isn't it going to be canceled out by what force, guys? By this force. So I could put that in, but it's just going to cancel out anyway. Is it okay if I leave it off? Yeah. Okay, so let's leave that off. I've also got this force, the force that B puts on C. But it's going to cancel out again. Which one's canceling this force out? The force that C puts on B. So again, these forces here are going to cancel each other out. So I'm going to leave them off. That's the only force that's going to the right was my force applied then. Now let's subtract off everything that was going to the left. So if I subtract off, which is basically all the frictions, right? So let's subtract off all these frictions. Let's start here with 9.8. We're going to subtract off the friction from block B, which was 13.5. And we're going to subtract off the friction from block C, which was 24.5. And that's going to give me the net force on this system. Now, the mass of this system, how do we calculate the mass of this system? Add them all together. So we got 5.5. Oh, sorry, we got 4 plus 5.5, that's 9.5, right? Plus 10, what is it? 19.5 altogether. So yeah, when you get to this point, this is for the system, so you need to add the masses of all of these blocks together. So 19.5. And then we're going to times it by A. And there's our equation. One unknown. So we can solve for acceleration that way. So let's simplify it. 120, subtract 9.8, subtract 13.5, and subtract 24.5 is 72.2 is equal to 19.5 times acceleration. To get acceleration by itself, we need to divide by 19.5, both sides. Cancels out on the right side, so acceleration is equal to 72.2 divided by 19.5. So the acceleration of this system is 3.70 meters per second squared. Did anyone get that? Yeah, good job. But it also wanted us to find, let me quickly put this back up. So we need to find the force that A puts on B and the force that C puts on B. Okay, so let's go ahead and find those contact forces now. If we're going to find the force that A puts on B, we see that right here. But if we have another unknown force, can we solve for it? No, so how can I find this one? The force that C puts on B. Won't it be the same as this one? Yeah, so what I would recommend, guys, is using this free body diagram first. Let's use Newton's second law, force net equals ma, just on this block by itself. That will give us the force that B puts on C, which is equal to the force that C puts on B. And then we can solve for this one because that's our only unknown force. Okay, I hope that you followed through there, but let's go ahead and do this. Let's do Newton's second law on this block specifically. So force net is equal to ma. The net force on this block, I'm going to call everything to the right positive, so that's the force that B puts on C. And let's subtract off everything that was negative, which was the friction here, 24.5. Okay, that will give me the net force. That is equal to the mass of it, which was 10 kgs. And we times that by its acceleration. We found the acceleration of that block was 3.7 meters per second squared. So let's simplify this. The force that B puts on C minus 24.5 is equal to 37, correct? How do I get this force by itself? Yep, we've got to add 24.5 to both sides, so 37 plus 24.5. Did you guys get that as well? 61.5 newtons, okay? Well, let's put that in our free body diagram. If this one is 61.5 newtons, what else can we fill in? Good, this one is also 61.5 newtons. Okay. So we've got the force that C puts on B, which was 61.5 newtons. Now, since we have this force, we can go ahead and solve for the force that A puts on B. But maybe there's an easier way. Could we use this free body diagram as well?
Yeah.
Could we solve for the force that B puts on A?
Yeah.
And wouldn't that be equal to that one?
Yeah.
And to me, this free body diagram looks a little bit easier. There's one less force at least. That's about the same, I guess. Anyway, it doesn't matter when you get to this point. You could solve it with Newton's second law on this block, or you could use this block. Okay, it doesn't really matter. I'm going to use this one right here. So force net is equal to MA. 120 is to the right. I'm going to subtract off 9.8. And I'm also going to subtract off the force that B puts on A. And that's going to be the net force, so that's equal to the mass, which was 4 kgs, times the acceleration. Again, it's the same acceleration, so 3.7. Let's simplify that. That's 14.8. 120, subtract 9.8. Is 110.2 minus the force that B puts on A is equal to 14.8. Okay, now I need to get this force that B puts on A, I need to get it to the other side because it's negative here. If we add it to both sides, won't it be positive on this side? Okay, so the force that B puts on A is equal to, so I'm going to move that over to the left. That means I need to move this 14.8 to this side. How do I do that? Minus 14.8. Good. And if you take 110.2 minus 14.8, what do you get? 95.4. 95.4 newtons. And so if that's the force that B puts on A, then we know that this force, the force that A puts on B, is equal to, but opposite directions, 95.4 newtons. Did anyone else get that? Can anyone verify that? Okay. So good job. Hopefully you figured out how to solve for those contact forces. It's not that hard. You solve for acceleration of the system first. Once you have this acceleration of the system, you can come back to these free body diagrams, individually use Newton's second law on them, and solve for these contact forces. So, good job. Okay, one more concept in this chapter, and it's this kind of problem right here. So practice problem number 21. I'd like to go through this one with you, and then you guys can do practice problem number 22 on your own. It says two boxes. M1 is 10 kgs, so this is the first box. And M2 is 4 kg, so this is the second box, are connected by a rope. So there's this rope right here. The 10 kg box is pulled with an applied force of 80 newtons. So this must be your applied force of 80 newtons. If the coefficient of friction is 0.1, it says to A, find the acceleration of the 4 kilogram mass, and B, find the force that the 4 kilogram block exerts on the 10 kilogram block. Before we start this, guys, what is the force that this block puts on this block? Isn't that right here? What do we call a force in a rope, string, wire, or cable? This is going to be tension, right? So that's kind of a clue to this problem. So let's go back. I'm going to take this off and find the acceleration of this 4 kilogram mass. So again, what I would like you to do is draw the free body diagrams for these separately. Okay, this is the 10 kilogram block. Force of gravity, what is it going to be on this block? Yeah, 10 times 9.8 is 98 newtons. That means the normal force up is also 98 newtons because it's not moving in that direction. It's got to be balanced. Okay, our applied force applied, is going to the left at 80 newtons. Well, if this system is moving to the left, guys, which way is friction going to point? To the right. So let's put friction in right here. So force of friction, and let's solve for it. What is, the coefficient of friction is 0.1. What's 0.1 times 98? That's 9.8. Okay, 9.8 newtons. And is there another force that's making this block or pointing to the right on this block? Yeah, that's tension, right? So I'm going to put T for tension. Okay, that's it for this block, all the magnitudes. I can't solve for tension yet. We will be able to at the end, though. Okay, let's draw the free body diagram for this block now, the 4 kilogram block. We got weight. What's 4 times 9.8? 39.2 newtons. Okay, that means my normal force up is equal to 39.2 as well. Okay, again, it's moving to the left, so which way is friction going to point? To the right. So force of friction, and that's 0.1 times 39.2. 3.92 newtons. Is there any other forces that are making this block or pointing to the right on this block?
No.
There's not, is there? What's making that block go to the left? Tension. Is there anything else?
No.
That's it. Okay. So there's our 2 free body diagrams. Now we're going to use Newton's second law to figure out the acceleration of this system. So force net is equal to ma. Your sign notation here is kind of important. I always like to call whatever way it's moving is positive. So I know that seems a little bit different because we said in physics everything to the left is negative, but it's just arbitrary. We're going to say that everything to the left on this problem is positive. Everything to the right is going to be negative. Again, because it's moving to the left. So my applied force here is going to be positive 80 newtons, so I'm going to put 80 here. And I've also got tension that's going to be positive. But isn't that going to be canceled out by this tension? Yeah. So I mean, I could put plus tension and then minus tension here, but they're going to cancel out. So let's just leave them off. That's everything that's going to the left. Now let's subtract what's going to the right. What are these forces that's going to the right? Friction. So I'm going to subtract off this 9.8. And I'm also going to subtract off this 3.92. Now that's going to give me the net force acting on this system, which is equal to the mass of the system. What's the mass of this system, guys? 14. Yeah, we got to add them together. So that's 14 kgs times the acceleration. Okay, there's one equation, one unknown. Let's simplify it. So 80, subtract 9.8. Subtract 3.92 is equal to 66.28. And that's equal to 14 times A. Divide both sides by 14. Cancels there. So the acceleration of this system is 4.73. What's the units for acceleration? Meters per second squared. Okay, can anyone verify that? Who got that? Okay, good job. Now, let's find the force that exists between these two blocks, which is tension. Again, how am I going to do that? How would I find tension, guys? I need to solve for tension. Couldn't I use Newton's second law individually on this block? Now that we know its acceleration, let's do that. Okay? So let's use Newton's second law on this block. So force net is equal to MA. Again, I called everything to the left positive, so I'm going to call this tension positive. So tension, now to get the net force we need to subtract off what's going the opposite direction, which was friction 3.92, is equal to the mass. Now I'm just taking this one individually now, so it's 4 times the acceleration which we just solved for. It was 4.73. Okay, so there's one equation, one unknown. 4 times 4.73 is 18.92. So tension minus 3.92 is equal to that. How do I get tension by itself, guys? Add 3.92. So tension is going to be equal to 18.92 plus 3.92. Are you guys getting 22.8 newtons? 8.4, but I'm just going to leave it out. So 22.8 newtons. Okay. It's always a good idea once you solve for one of those missing forces to plug it back in here. So this one's 22.8. Is it still going to have a net force to the left? Yeah, this is way bigger than 3.92, so it's going to go to the left. And if tension here was 22.8, if we add that to 9.8, is it still going to move to the left? Yeah, because 80 is much larger. So the physics makes sense. Guys, this is the physics of like trains. So if you worked for a railroad, you could figure out if you were on this project how much tension would be in the connectors between the two rail cars, couldn't you? Once you knew the tension, would you know how much material you would need to use to make the connectors with? They've got to withstand that much force. And so there's some applications to this kind of stuff, and hopefully you see that. I've got one more problem for you. Practice problem number 22. Okay? There's 3 objects this time. M1 is 10 kgs. M2 is 20 kgs. And M3 is 15 kgs. They're tied together by a rope and pulled along a level surface by an applied force of 150 newtons. So this applied force is 150 newtons to the right. All 3 objects have the same coefficient of friction, which is 0.25. It wants you to solve for the acceleration of the system and find the tension in the ropes connecting the masses. So there's going to be tension here, and there's going to be tension here. So let's call this one T1 and this one T2. So I want you guys to try this one on your own. Please, if you're watching the video, hit pause now and try to see if you can solve for the acceleration of the system and the tensions in T1 and T2. So please try it, see if you can get an answer. Once you do have an answer, hit play and see if you got it right. Okay guys, let's see if you did it right. I went ahead and drew the free body diagrams for these M1, M2, and M3 separately. So actually let's start over here with M3. We've got an applied force of 150 newtons, so hopefully you drew that in. The weight of this is 9.8 times 15, which is 147. That means the normal force has got to be 147. And since this whole system is being pulled to the right, friction has got to be going in the opposite direction of motion, so it's going to the left. You find friction by taking 0.25, our coefficient of friction, and timesing it by the normal force. You should get around 36.8 newtons. Okay? But there's one more force that I left off. There's another force going to the left on this free body diagram. What force is going to the left here? Tension. Okay? And that's the tension that exists in this rope here, which I call T2. So I'm just going to call it T2. Okay? And that's all the forces on this M3 block. Okay, how many of you guys got those right? Okay, good job. Let's go to the middle rail car now, M2. again, I like to start with weight, which is 20 times 9.8 is 196 newtons. That's got to be your normal force up. Since it's going to the right, friction's going to the left, we take 196 times it by the coefficient of friction, which is 0.25, to get 49 newtons. But I left off a couple of forces here, guys. Please pay attention. What force is making this block, M2, go to the right? That's called tension number 2, right? So I'm going to call it T2. Is there another force that's pointing to the left on this block, though? So is there another force that's making or pointing to the left on M2?
Okay.
And the answer is yes, it's tension, right? Tension number 1. It's the tension that exists. This block here is going to be pulling M2 to the left. So I'm going to put T1 right here. Okay, and then finally, let's draw the free body diagram for M1. Start with the weight, which is 98. So it's because 10 times 9.8 is 98. The normal force is 98. If you take the normal force and times it by 0.25, you're going to get 24.5, and that's what friction is. Again, friction is pointing to the left because this whole system, this train, is moving to the right. But there's one more force that's making this rail car go to the right. What is it? What is it, guys? Isn't it T1? It's the tension in this rope that's pulling that rail car to the right. Okay, so I hope that you could figure out the free body diagrams for these 3 rail cars here. Now let's go ahead and answer the question, what's the acceleration of the system? Whenever you see the word acceleration, you should think force net is equal to ma. Let's call everything to the right, let's call that positive, and everything to the left is negative because it's moving to the right. So this applied force of 150 newtons is to the right, so I'm going to say 150 is positive. Okay, isn't T2 going to be positive as well? But is that going to be canceled out by this T2? Yeah, these are going to be equal but opposite forces here, so I'm not going to include them in my net force. Okay, is there anything else going to the right? Well, T1. But is it going to be canceled out by this T1? The answer is yes. So now let's just subtract off everything that's going to the left, which is my frictions. So I'm going to subtract off 36.8. And I'm going to subtract off my 49 newtons for friction there. And I've got one more friction down here, 24.5, that I've got to subtract. Okay, that will give me my net force, which is going to be equal to the mass times the acceleration. But be careful here. The mass is for the system. What is the mass going to be for the system? What's 10 plus... So this 10 plus 20 plus 15. What is that, guys? 45 kgs. And that's going to be times by the acceleration. So now we have an equation with just one unknown here. We can solve it. Okay, so let's simplify it. 150, subtract 36.8, subtract 49, and subtract 24.5. So 39.7 is equal to 45 times A. If we solve this equation now, we'd have to divide it by 45 both sides. So my acceleration of this system is 0.88 meters per second squared. How many of you guys got that? 0.88 meters per second squared. So all 3 of these rail cars are going to accelerate at 0.88 meters per second squared. Okay, that's key. Once you find the acceleration of the system, can I then go back through and solve for the tensions here and here? And the answer is yes. So how do we do that? Well, we're going to use Newton's second law individually. Let's use it for this first rail car here, or M3. If we use Newton's second law on this one, can we solve what T2 is going to be? Sure. So let's do that. I'm going to do it up here. So force net is equal to MA. I'm calling everything to the right positive, so 150 is positive. And I got to subtract off everything to the left, which is tension 2. And I've also got to subtract off the friction, which is 36.8. Okay, that's going to be times by the mass. Now, we're not doing the system anymore. It's just for this one block, so it's 15. And do we know the acceleration? The answer is yes. It's 0.88. Okay, so let's simplify that and solve for T2. So 15 times 0.88 is 13.2. Let's try to simplify this as much as we can. So 150 subtract 36.8 is 113.2 minus T2 is equal to 13.2. Guys, when you get to this point, we need T2 to be positive. So I need to move it to the other side. How do I do that? Don't I have to add T2 to both sides? Over here it cancels out. And if I want to get T2 by itself, what have I got to do to this 13.2? I got to subtract it from both sides. So if we take 113.2 and subtract 13.2, what does that equal? Isn't that 100 newtons, guys?
Yep.
So this force right here, T2, is 100 newtons. Well, can I put that in right here for this T2 as well? And the answer is yes. Okay, so I've solved for T2, which was 100 newtons. Now let's solve for T1. Guys, which free body diagram looks easiest to solve for T1? And I would say this free body diagram. So again, let's use Newton's second law on this block specifically and solve for what T1 is going to be. I'm kind of running out of space. Let me move this over. Let's do it right here. So force net is equal to MA. I'm calling everything to the right positive, so I'm going to call T1 positive. And now let's subtract off everything that's going to the left, which is friction 24.5. That will give me my net force. The mass of this block is 10 kgs. And times it by the acceleration, which we found earlier to be 0.88. So let's simplify it. T1 minus 24.5 is equal to 8.8. So that means T1 has got to be equal, if we got to add 24.5 to both sides. And that's 33.3 newtons. Okay, so T1 is 33.3 newtons. It's always a good idea to plug that back in, 33.3 here and 33.3 there. Would this train car still accelerate to the right, guys? And the answer is yes, because 33.3 is greater than 24.5. Okay. Anyway, so that's the last question on this chapter. Guys, did we understand it?
Yeah.
I hope so.
Yeah.
This is kind of train physics, so you can figure out all the forces that exist in a train, right? Could you answer a question like this on the test? I hope so. Guys, to give you more practice, there's a worksheet in your student workbook. It's called Two-Body Force Worksheet. Again, that's called Two-Body Force Worksheet. Please head there and see if you can complete those. And hopefully this video helped.